The laws of thermodynamics are a set of fundamental principles that govern the behavior of energy and matter in the universe. These laws form the foundation of the study of thermodynamics, a branch of physics that deals with the relationships between heat, energy, and work. There are 4 laws of thermodynamics, but the first 3 are the most commonly referred to. Let's explore each of these laws. 1. Zeroth law of thermodynamics. If 2 systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This law establishes the concept of temperature and is the basis for measuring temperature using thermometers. It implies that if 2 objects are in equilibrium with a third object, they must have the same temperature. 2. First law of thermodynamics, law of energy conservation. Energy cannot be created or destroyed in an isolated system. It can only change forms from one type to another. The first law is often stated as energy is conserved. The total energy of an isolated system remains constant, and energy can be transferred as work or heat between the system and its surroundings. Mathematically, the first law is expressed as delta U equals QW, where delta U is the change in internal energy of the system, Q is the heat added to the system, and W is the work done by the system on its surroundings, or vice versa. 3. Second law of thermodynamics. The total entropy of an isolated system always increases over time and remains constant for reversible processes. Entropy is a measure of the system's disorder or randomness. The second law states that natural processes tend to move towards higher entropy, leading to an increase in the overall disorder of the universe. While the entropy of an isolated system increases, it remains constant for reversible processes, where no net entropy change occurs. The second law also introduces the concept of heat transfer, spontaneous processes, and the direction of time. 4. Third law of thermodynamics. As the temperature of a system approaches absolute zero, 0 Kelvin or minus 273.15 degrees Celsius, the entropy of the system approaches a minimum value. The third law implies that it is impossible to reach absolute zero in a finite number of steps. At absolute zero, the entropy of a perfectly ordered crystal is considered to be zero. These laws of thermodynamics have far-reaching implications in various fields, from engineering and chemistry to biology and astrophysics. They help explain how energy behaves and transforms in various physical processes and play a fundamental role in understanding the behavior of matter and energy in the universe.